Hi, welcome back to our radiation heat transfer learning journal. Yes, I think there's a mistake in the last video that I'd like to correct. Yeah, there should be a wavelength at the bottom here. So it depends whether you want to use a wavelength basis, wave number basis, or frequency basis. You should have that at the bottom. So I'll need to put all this in to make it sure. Make sure it is that amount, yeah. Alright, so how do we quantify the power contributed to this system by the third ray? Okay, and alright, so what is that power being contributed to? Well, there are two ways. I mean, we can just take a look at the textbook, and then I'm just going to go through that. Or of course, yeah, it's basically the same content. I can either read off here, or we can draw a diagram. So let's first consider what radiation is coming through this in this via this direction J. Okay, so let's zoom in. I'm going to clear up some things. Alright, so let's again draw the surface dA here. Okay, so and then this is ds, right? ds. And you just imagine there's a 2D surface on the right for dA. Okay, let me do this, and yeah, magnifying glass. Okay, so normally the radiation comes in at a very straight angle. Okay, the angle of incidence is pretty much 0. It is normal to the surface, so this is what normally the radiation comes in. Radiation normally comes in like that if you were considering the main direction. Okay, but in this case, radiation comes in from this oblique angle. Right, this oblique angle. Let's call this angle theta. Alright, so what is this intensity coming in? So it's I lambda in the j direction. Okay, so let's just put a j here because it's going in this some other direction j, which is not I. So yep, some other direction j. Okay, so what is the frequency? Okay, let's make that lambda a little nicer looking. There you go. So the energy, okay, in that frequency range, you can just put a d lambda there. Sure. What else? We will also need the solid angle. So we take this small pencil of rays coming from this specific solid angle. Okay, it's just this direction, so that's what we need to do. So I can put a d omega j. Alright, to differentiate it from this other pencil of rays here. Okay, this pencil of rays entering the system here. These are different solid angles. Then what's the area? What's the normal area? So this is energy power per unit wavelength per unit solid angle. So I've already defined the solid angle as this little d omega here. Right? That's the little solid angle there. What's the area? Or what's the normal area? Is it just dA? No, it's not just dA, but dA is definitely part of it. You just have to correct it by a certain factor. So we notice at 90 degrees, or rather at theta equals to 0. At theta equals to 0, dA, this normal area is just dA. But once it's off 90 degrees, we will need to do something. We will need to do some trigonometry. So normally what we do is just have the cosine of the theta, right? Cosine theta. Why is it cosine theta? Okay. So let's do some trigonometry. Yep, the normal area, it is this much, right? This little red line here. That's what the normal area is. Okay, so there we go. And where then can we find this theta? Right? Theta will be the same here. Okay, how do we know that? Again, need to do some little trigonometry here. This is theta. This is 90 degrees. Okay, I'm going to do this. It's 90 degrees, and this is 90 minus theta, and this is theta, this green angle up here. So if we want the normal area, what I'm highlighting in green now, we need to do a cosine theta to it. So this is the total amount of energy impinging on this in this control volume, right? So it is this intensity, which is the energy per unit wavelength, per unit solid angle, per unit normal area. So this is the normal area that it's being considered. So let's put that down first. The energy coming in is, okay, I lambda j. If I were to go and put it, if I were to name it as such that way. Next thing is the d lambda. Okay, d lambda, and d omega j. This is the infinitesimally small pencil of rays from this direction, right? From this solid angle specifically. And then we'll have this cosine of theta, right? Cosine theta. That is the normal area, depending on the angle of incidence of this ray. I mean, no matter what, depending on how you rotate it, even if it's 3D, this ray can be kind of pointing to you, but you just measure theta between the normal. You just measure the angle between this normal to the surface and the direction of the incoming ray. You get theta, no matter how you rotate it around. So let's say this is a normal angle. Then you have theta coming from here. That's one of the ways, one of the rays. But let's say this thing is kind of pointing away from you and kind of pointing away. You can also measure theta like that. So doesn't matter if it's 2D or 3D. I mean, doesn't matter if it's 3D, this relation still holds. Okay, it's just this, as long as this theta is the angle between the normal and the direction of the ray coming in, it should be okay. So right, the energy coming in there is dA. I mean the normal area there is. Yeah, the normal area is dA cos of theta. Okay, dA cos of theta. Alright, so this is the theta here. Now of course, this ray is going to go through this system. Okay, the ray is going to go through the system, through this little purple length, and then it's going, some of it's going to exit this system. Alright, and what's going to happen like that then, from here to here? Same things can happen, and since we are more concerned about scattering in this case, we are interested in how much of this energy is, or of this ray, how much energy is being scattered from this direction, this J direction, into the primary direction we are concerned about. So what's the scattering? How much energy is being scattered in this direction? Okay, so that's the in-scattering. So it's scattered from some arbitrary direction J into this primary direction. So when you talk about scattering, how much energy is being scattered? Alright, and then how that will be subtracted from the amount leaving. So the amount that is scattered is what we are concerned with. Alright, so how much energy is scattered? Okay, so I'm going to leave this here. Okay, so let's go back to the scattering equation that we have. Okay, so di ds scattering equals to I lambda into sigma. Okay, so di ds scattering equals to this. So we apply this equation, right? So yeah, so this, what do we do? You substitute the I lambda, this is the ray in question anyway, with this. Okay, we'll have to multiply all of this throughout first. So we are multiplying this throughout to both sides, just to make the units consistent. And then I'll just have this here. So actually this is the amount scattered. Right, this is the amount scattered. And if you want to separate the variables, I mean, if you want to get the more exact amount scattered, because it does depend on how long this path is. So I mean, of course, the longer the medium, the longer the path of the ray being that's traveling through the system, the more that's being scattered. So let's copy and paste. The I lambda outscattering, okay, is equals to, so we just multiply the s to the other side. Alright, and then we kind of have to find out what is this ds. So what is this ds here? So let me just put a highlight here. So ds, remember, we were talking about is the, in this context anyway, in this context of this equation here, it is the length with where which this ray actually travels through. So when it travels through this little control volume, it does not travel this full length, this yellow colored ds here. It actually travels slightly shorter than that. So how long does it travel? Okay, so we'll need to do something here. Again, we need to consider the angle of incidence. So this is, let's see, this is theta here. Right, there is theta here. So we want to kind of find out this little length. Okay. So it does not quite travel the full distance. So how much distance has it covered? Well, if you do your little trigonometry thingy, you know that this is a right angle because this should be normal. Okay, it should be normal. So we can see that this length here is ds, and here is just this length that is traveling through is ds cosine theta. So you see this cosine theta term comes up again. Alright, this the ds cosine theta comes up again. Oh, let me correct myself. Let's try that again. I did something wrong there. So yeah, what is this amount before, what's the length traveled before it exits to the other side? Sorry, so this is ds, this is correct, this is ds. So it has to exit through this boundary, not this boundary here. So I kind of got that wrong just now. So the path actually traveled before exiting this small little section called ds is this long path. Alright, that is this long path. So this is ds, and the path traveled is actually this much. So while this beam is traveling through this control volume, dA ds, I mean it has, I mean the scale is kind of a little off, but I mean dA can be this this whole area here. Alright, it's not just this small little area there, but you get the point. Yeah, because we need to encompass all the rays that are coming in. Anyway, so the boundary where it's exiting is where I circled here. So the path traveled is not ds, but ds, the length here that's being traveled, the length that's being traveled, or rather let's put ds equals to this length traveled, and you put cosine theta here. So what the length traveled is just ds over cosine theta. Okay, so it does not exit the control volume here as we define it. It exits the control volume here. Okay, why is that? Yes, why is that? So I suppose the reason is because we are concerned with this ray in the first place. We're concerned with this primary ray, direction I. This primary ray will travel distance ds through this system, and during the course of travel, from this s to s plus ds, during the course of travel from s to s plus ds, the number of things can happen, the four effects can happen. Effects, so it's scattering. Okay, let me type in scattering. Oh no, I'll use this, it's much better. So outscattering. So it's outscattering, absorption. Okay, outscattering and absorption can happen from here to here, but also the emission let me write that properly. S-I-O-N and inscattering. Okay, so its emission and inscattering can happen from here to here. Alright. So if the ray, we stop considering the ray here, then okay, so if the ray is coming from here to here, there'll be outscattering, there'll be absorption, there'll be inscattering. Alright, because we consider that the ray is only getting scattered in from here to here to change direction here. Alright, but suddenly if we say this ray, we don't consider this ray anymore after this point, then from here to here, the only effects happening are outscattering, absorption, and emission. There's no more inscattering anymore. So we have to consider that the boundary only, the ray only exits here, so the total, so that all throughout, all these four physical effects are happening to the primary ray traveling at this I, traveling in direction I. So yeah, the distance is slightly longer from here to here, and it has to exit at this point, so that as the ray travels from here to here, it can still get scattered into the primary direction, which is here. Okay, so we have discussed that, okay, the ray being the ray that's being scattered from a different direction, it travels a length L, and that L is ds over cosine theta. So I'll have to replace this ds, which is not the same ds as this. This one have to be ds divided by cosine theta. Right? So yeah, so what happens after that? We realize that something interesting happens. The amount that's being outscattered, okay, the cosine thetas kind of cancel out, which is kind of convenient, and the amount of radiation that's being scattered will be this quantity here, the amount of energy being scattered. All right, so like I was saying, when radiation travels through this little medium, through this length, the amount being scattered is this much. So the next question is, how much of this scattered radiation goes into this direction? So that will be the subject for the next video. I'll see you guys next time.